Okay, so this is an example problem from 3.6, which basically takes everything from 3.1 to 3.5 and kind of sticks it into one problem. We'll have a y value. This is y equals x over an x squared plus 16. And what we're going to have to do is find the first derivative, the second derivative, and use the values that we find in there to plug back into y equals so that we can find the intercept, the min, max, points of inflection. For the asymptote, we're going to have to just use our rational expression rules for the very original and go back and find the asymptote from there. So first thing we'll do is I'll find the first derivative. I let x be f of x and g be the x squared plus 16, so that I have x squared plus 16, that's squared. G times f prime minus f times g prime, and that one really wasn't too bad. It turns out to be a negative x squared plus 16 over x squared plus 16, that quantity squared. So there's my first derivative. Now I need to find my second derivative. I'll again let him be f and this guy be g. So g squared will now be x squared plus 16 to the fourth because I'll square the square. G times f prime, so a negative 2x, minus f times g prime, so drop the 2 for 2 times the quantity x squared plus 16, and then we got to use chain rule, so derivative of the inside, which is going to be a 2x. Clean this mess up. I took, it looks like my 2x, my 2 and my negative from out here and made him into a negative 4x. And then what we can do is divide out one of these x squared plus 16. So now there's 3 left down here, only 1 left here, and this one divides out completely. So that way now I can send through this negative 4x to get a positive 4x cubed minus 64x. Then finally send this negative 2 through, negative 2x through, and combine some like terms, and you get a not so pretty y prime of 2x minus 2x to the third minus 96x all over x squared plus 16 to the third. So we're going to take those two pieces and finally start the problem. So for my intercept, you just let x and y be equal to 0. So if I want to know where I'm going through the x-axis, that means y is equal to 0. When you set this original f of x equal to 0, basically you're just left with x equal to 0. Plug that into your f of x to find y, so 0 over 0 plus 16. My intercept is at 0, 0. Now to find the min and the max, you're going to do that with your first derivative, and your first derivative was negative x squared plus 16 over the x squared plus 16, that quantity squared. Again, when you cross multiply, basically your denominator drops out and you have this guy equal to 0. When you bring over the 16, you get a negative 16, or you can bring over the x squared, get a positive x squared. You have x at positive or negative 4. Again, take those, plug them back into the originals for the 4x, the original f of x. So I have 4 over now a 16 plus 16, a 1/8. Then a negative 4, that negative will square out, so it's still 16 plus 16, and I have a negative 1/8. So those are where my mins or my max are. The lowest y value is your min. So that would be the negative 4, negative 1/8, and the highest y value is your max, so that's going to be our positive 1/8. Sometimes you have more than one, and they're not the min or the max, and it has to be the highest and the lowest. So if you have multiples, they may be peaks and valleys, but they're not the lowest and they're not the highest. And so we have these first 3 done. And that was basically 3.1, 3.2, maybe a little bit into 3.3. The next part is points of inflection. And so now you're going to take your second derivative, set that equal to 0, and again your denominator zeroes out. So I have a 2x to the third minus 96x equal to 0. Factor out my 2x, so I got x equal to 0, and unfortunately over here you got a positive negative square root of 48. So that is where, somewhere in between your peaks and your valleys, even though you're always going to be increasing along that domain or always decreasing along that domain, at some point your ceiling becomes your floor, right? So if you're like this, going from this valley to this peak. At some point through here, we say you're no longer a part of this bottom U, but then become part of this top like end piece. So over here, we consider this part my ceiling, but once you get past this part, well, now here's your floor. And that's going to be your point of inflection. So I have 3 points of inflection that I'm going to have to plug into my original. And one of them is going to be at the 0. Plug in the 0 to the original, you still get out that 0, 0. You plug in the negative radical 48. That's the smallest of the 3 numbers, so that will be my smallest point of inflection. You get a negative radical 48. When you square that, you're just with a positive 48 plus 16. So a negative radical 48, I can't write that small in this little box, over 64. 0, 0 is going to be in between because my next and my largest number is actually a radical 48. And that will be a radical 48 over now the positive 64. Because now he stays a positive up there. So I have these 3 pieces. For your asymptote, we have all of this information now. For the asymptote, we're going to have to only look at my f of x and use my 3 rules. So for this one, my numerator degree is a 1 and my denominator is a 2. So my numerator degree is less than my denominator degree. So when you have that, you're automatically at y equals 0. Had it been the other way around, where my numerator degree is higher than my denominator degree, which you do have happen in a couple of problems in 3.6, what you're going to have to do is get it to be all together because they kind of have it mixed up. I think a lot of them kind of look like something like this. You're going to have to put this into one problem and then actually do the polynomial division. And what you get out for a quotient, that's going to be the equation of, in most cases, the line, but it could be the equation of any kind of a graph that will give you the slant asymptote. And for a lot of these, they turn out to be y equals x. Had they been the same, like a x squared over the x squared plus 16, then it's going to be y equals the quotient of the leading coefficient. So if you have like a 2x squared and like say a 3x squared minus 1, it would be at y equals 2/3. I didn't see a lot of those. I saw a lot of the first scenario and the third scenario. The last part just says verify your results with the graph, and what you're going to have to remember to do is zoom fit because it will show on WebAssign. I think this max is either a 0.5 or a 0.5, whatever it was really small. So when you graphed it on the standard scale, it just kind of looked like a straight line, but you knew it couldn't be a straight line. And so when you do zoom fit, then you finally get that. So you'll be able to see, all right, so here's my -4, right, for my minimum. Here is my +4 for the maximum. I have no idea. Radical 48. 48. Radical 48 is about a 6.9-ish. So over here is my negative radical 48 for my point of inflection. Here will be like, let's see, 4, 5, 6 over here, maybe positive radical 48 there, and then of course the 0, 0 in between. So at 0, 0, we say we're no longer, even though it's increasing along this whole domain from -4 to +4, at this point we say, all right, these numbers are part of this, and then from the 0, then it will be a part of that. For that part of the domain will be that part of the graph. That's how you pretty much do them all inside of 3.6. This screen and all of the other screens, I have them uploaded as a PowerPoint. I think the PowerPoint looked better than the PDF, and so that way you can kind of scroll back and forth between the video and the example.